record. And then I'm going to introduce Justin. It's my pleasure today to introduce Justin Pflug, who got his Bachelor of Arts in Physics in 2016 from Hastings College. He then came to the University of Washington, where we promptly handed him a whole bunch of rebar and PVC pipe, and he had to carry it 17 miles into the wilderness of the Olympics, and which he did with a smile. And that led to his master's thesis on percolation of water through snow in the Olympics, and to him participating in the Future Park Leaders of Emerging Change as an intern in the Olympics, working with Bill Bacchus in summer of 2017. After that, he went and he visited Glenn Liston in Colorado to learn Snowmodel. We may have done that in the middle, maybe I got the order wrong. And he also visited the Swiss Institute of Snow and Avalanche Research in Davos, Switzerland. Came back, used everything he learned to do a whole bunch of LiDAR analysis, a whole bunch of modeling. And he has, not to like overinflate your expectations today, but he has won 2 Best Poster Awards and 3 Best Presentation Awards in terms of presenting this research at various conferences around the country. And so I'm very, very excited to hear Justin present, and I will turn this over to you, Justin, to share your screen.
Okay. Let's see here. Can everyone see my slides now? Sorry, it's slow. There we go. All right, are we good to start? Okay, great. Thank you so much, Jessica, and also thank you everyone for being here. It's really exciting to see such an awesome turnout. Really before diving into this, I want to recognize a bunch of people, specifically my PhD committee listed here, some of the co-authors on this work, and some of our sources of funding and other groups that we collaborated with as part of this work. Also for the University of Washington area, I want to start with the land acknowledgement. Specifically, I acknowledge the ancestral Coast Salish peoples of this land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Now in this presentation today, I'm really going to be covering my whole dissertation and really hitting on this idea of snow patterns and how we think we can use historic information provided to us by these snow patterns in order to better hone our estimates of both snow volume and heterogeneity in mountainous terrain. But before really diving into this, I kind of want to start with an introduction and kind of explain some of our motivation for this work. So if you've ever been out in a mountainous watershed in the winter, you may have noticed scenery that looked a little bit like this. And specifically, while the amount of snow or the snow volume from year to year can change, what you may notice is that in space, snow can be very spatially heterogeneous, and sometimes these features reappear year after year after year. So when we're talking about heterogeneity or the placement of snow, it's largely dependent on the spatial scales that we're talking about it. So for instance, at very fine spatial scales, things like wind redistribution or snow creep or canopy interception can actually influence the heterogeneity of snow. And when you go to larger spatial scales, different processes start to emerge. We're talking about things like wind-aided preferential deposition, or there's more lateral transport from things like avalanching or snow sloughing. And this can scale all the way up to very large spatial scales, say a kilometer in length or greater, where the distribution of snow accumulation tends to be a process of the snowstorms themselves. So we're talking about things like the size, timing, orientation, frequency of these snowfall events, which can control total snow volume and things like snow elevation lines. And of course, how snow is distributed in space is not only a function of how it accumulates, but also how it depletes. And these snow depletion processes act on a variety of spatial scales as well. So why do we actually care about both snow volume and how it's distributed in space? So to provide an example, let's assume that we have some mountainous terrain shown up here on the left, and across that terrain, we represent our snow in 4 grid cells, shown by these black boxes. And for the purpose of this demonstration, let's assume that we have 2 cases with equal snow volume, but one with snow that's more homogeneously placed in space, and one that has more heterogeneous snow placement. And if we assume some, spatially homogeneous melt energy, we can actually look at how these two cases evolve throughout time. Specifically for the homogeneous case, you see this maybe less rapid snow melt early in the season, followed by this more rapid snow melt late in the season when snowpacks are thinner and energy is typically a bit higher. But if we add the heterogeneous case to this, we see a pretty significant difference in how snow evolves throughout snow melt. And specifically what we notice is this more incremental disappearance of snow across the landscape as snow disappears first at these thinner depth grid cells, but yet persists much later into the snow melt season at these deeper snow deposits as these grid cells take much more energy to bring the snow to this right melting condition and therefore lengthen the duration of the snow melt season. And this is really important, especially for the Western United States, where these spring periods are usually characterized by warmer and drier conditions. So water provided by snowmelt during these periods could be important for things like agriculture, municipal water supplies, or fish flows. So we as snow hydrologists really want to be able to actually capture and model our snow across our landscape. And when I talk about a model today, a simple way you can kind of think about this is just a system of equations that are intended to represent the physics of how snow accumulates and depletes in space and time. And these models are usually provided information about the weather in space and time. This is called meteorological forcing. And this can include things like air temperature, relative humidity, wind speed, precipitation, both rainfall and snowfall. So using this combination of forcing and a model, we should be able to actually simulate snow in space and time. So for example, what I'm showing you here on this plot is snow simulated at a point from October to June. This top line represents the temporal evolution of snow depth, and the bottom line represents the evolution of SWE, or snow water equivalent. A simple way to think about snow water equivalent, it's simply the depth of water that would exist if your snow were to instantaneously melt. So these are terms I'm going to be using frequently throughout this presentation, in addition to this term called snow density. And a way to think about snow density is just, it's the amount of water that exists per unit volume of snow. So, for instance, in this early April period, we see that the snow at this time is about 30% water or 30% snow density. So despite our need to actually simulate snow in space and time, we really struggle to do so oftentimes in these complex mountainous landscapes. And part of our issue is driven by issues with meteorological forcing. So specifically what I'm going to be talking about today is issues with snowfall, which is the most commonly cited source of snow model errors. And in fact, in the regions we're going to be looking at today, some commonly used meteorological products have noted biases in snowfall of up to plus or minus 60%. Yeah, even if we do have an accurate estimate of mean snowfall, sometimes we still struggle to model the spatial distribution of snow in mountainous landscapes. And more often than not, this is driven by either mismodeled or unrepresented snow processes. We're talking about things like wind redistribution or avalanching that are more complicated to model. And as a result, this often results in snow modeled in space as too spatially homogeneous. And as we've seen, that can have an impact on our rate and timing and duration of spring snowmelt. But fortunately for us, as I've already discussed, how snow is distributed is a function of these overlapping snow accumulation and depletion processes. And these processes often rely on things that sometimes repeat from season to season. We're talking about things like prevailing storm directions or static features like terrain and vegetation. And as a result, in many mountainous regions, we see patterns that emerge from year after year after year. For example, what I'm showing here is satellite imagery over a region in the California Sierra Nevada between 3 years with very, very different snow magnitude, but as you can see, similar snow placement. So in this research, what we really wanted to do was ask the question, can we use this information provided to us by historic snow patterns? And specifically, can we combine these with our current snow modeling efforts and some real-time observations that become available from things like ground-based or airborne or satellite observations. And combining all these resources, can we better hone our estimates of both mean snow and snow spatial heterogeneity in this complex mountainous terrain? So as part of this presentation today, I'm going to be focusing on the California Sierra Nevada, shown here on the leftmost plot. And specifically, I'm going to be focusing on the Upper Tuolumne River watershed in I-70 National Park in the central Sierra Nevada shown here. I'll be looking at that domain in chapter 2 and 3 exclusively, and then expanding to include the Northern Sierra, Sage Hen Creek watershed, and Southern Sierra to Upper Kings watershed in chapter 4. So great, with this background, in chapter 2, we really wanted to start from the ground floor and ask, given the observations that we have at our disposal in these domains, are we even seeing that snow depth patterns are repeatable from season to season? And if so, can these historic patterns be used to infer real-time mean snow depth and snow depth variability? Before diving into this, I really want to mention that this is part of a manuscript that's published at Water Resources Research that was published in 2020. So as I mentioned, we're going to be looking at the Tuolumne River watershed, shown here on the left. And we're really looking at this domain because of the huge prevalence of airborne LiDAR snow depth observations that we have here. So for those of you who aren't familiar with airborne LiDAR, this is simply a laser, in this case, flown from a plane, that tracks the amount of time for a pulse to emit, hit off a surface, and return. Then using precise information about where that laser is and how it's pointing, you can actually map the elevation of the terrain at very fine spatial resolutions. And this is done once during a period in the summer without snow. And it's repeated in periods with snow later in winter. And simply the difference in elevation between these winter periods and your summer periods is what's used to calculate snow depth at very fine spatial resolutions. So for instance, looking at this smaller subdomain in the Tuolumne River watershed here outlined in yellow, what I'm showing here is LiDAR observes snow depth observations from periods near peak snowpack timing in 4 different years. And what you may notice right away is that between these 4 years, there's very big differences in the actual snow magnitude, right? There's differences in total snow volume. However, in this study, we were really concerned about the spatial distribution of these increases and decreases in snow depth. So what we want to do is find a way to actually normalize these snow patterns. And we did that using what's called the standardized depth value, or SDV, where we normalize snow depth at every grid cell based on its departure from mean snow depth, divided by the snow depth standard deviation across the domain. So what we can see is that by doing this, what was originally very different snow depth maps of different magnitudes, some of these years started to approach very similar snow patterns or spatial increases and decreases in snow depth. So if we actually have snow patterns from season to season that persist, this suggests we should be able to use some real-time observation, say a strip of LiDAR observations across a portion of the domain, and use a snow depth pattern, the relationship with that snow depth pattern in a different year to actually infer snow properties like domain mean snow depth and snow depth standard deviation. Then using those properties of mean snow depth and snow depth standard deviation and a pattern, we should actually be able to infer snow depth in locations where it was not actually originally observed. So for the purpose of this demonstration, I'm going to talk you through one test we did. Specifically, we took a strip of LiDAR snow depth observations on 7th of April, 2014, and calculated inferred snow depth maps using snow depth patterns from all other years, all other LiDAR observations in other years that we had at our disposal. This included 37 snow patterns. Then using those 37 different inferred snow depth maps, we actually fed these into a radiation-based snowmelt model and simulated basin-wide snowmelt or total Tuolumne-wide snowmelt every day throughout the snowmelt season in 2014. And here I'm showing snowmelt in acre feet per day, and this can simply be thought of as the amount of water it takes to fill an acre-sized swimming pool with water a foot deep. Also, what I'm showing here in the black line is a baseline simulation that we set up independent of this, that we know actually reproduced the depletion of snow very well in this domain. So this is our best estimate in this location in here. So to hop right into the results, what we found is that when we inferred snow depth using snow depth patterns from periods with really different seasonal timings and different snow extents, in other words, patterns that weren't representative at all of 7th of April, 2014 snow depth, our simulated snowmelt diverged pretty widely from this baseline simulation. Specifically, we intended to infer snow depth that was too spatially homogeneous. And as a result, we overestimated early spring snowmelt and greatly shortened the length of the duration of the snowmelt season. However, as we went into our patterns and picked more and more representative snow patterns, say from periods near peak snowpack timing in other years, what we tended to see was that our simulations of snowmelt started to approach this baseline simulation much closer, and specifically during this late summer period where snowmelt, water from the snowmelt is so crucial. So to briefly kind of wrap up what we did in this chapter, we found that snow depth patterns between periods with similar proximity to peak snowpack timing, similar snow extents were very, very repeatable, and we could even get a little bit better by going after years with more similar meteorological conditions. Overall, we could infer snow depth mean and variability really well using a snow pattern from a different year, and snow depth observations covering only a portion, less than 4% of it, in this case, of the Tuolumne watershed. And as shown before, we showed that these the volume of snow and the heterogeneity at peak snowpack timing greatly influenced the duration and timing of spring snowmelt. So great. So in chapter 2, we showed that we could combine these real-time observations of snow depth and snow depth patterns from different years to really estimate snow in space. But what if these real-time snow depth observations, say from a strip of LiDAR observations, aren't available to us? We next wanted to ask, can we actually use these patterns in our modeling efforts? Specifically, can we scale the input of snow input in space as a substitution for these processes that aren't always captured by models? So in this chapter, or I should mention that this chapter is part of a manuscript that was submitted to Water Resources Research and is in revisions. And as I mentioned before, we're going to be focusing on the Tuolumne River watershed, and specifically over these 3 smaller subdomains located over the Stubblefield, Matterhorn, and Lyell canyons. What I'm showing here on the right are LiDAR observations of snow depth that we have at our disposal, again, on 7th of April, 2014. And our goals in this research were really to actually reproduce these snow depth observations using a model-based approach and using a model actually called Snowmodel. And it's important right here to acknowledge that Snowmodel does actually calculate wind redistribution of snow in space. However, for the purpose of this experiment, we actually disabled this wind redistribution and instead attempted to scale our snow input in space manually as a substitution for this process. And I'll talk about that a little bit here later on. Our meteorological forcing in this simulation came from the Weather Research and Forecasting Model, or WRF. And it's important to mention that WRF was restricted to represent the land surface at 6 kilometer spatial resolution, which was approximately the size of each of these modeling domains here. So to put this another way, we know that the terrain was significantly more rugged at finer spatial resolutions, as shown by the surface. And we know that the heterogeneity of snow input across this terrain varied on 25 meter spatial resolutions. However, WRF was constrained to represent this whole region by some mean elevation, as shown by this shaded plane, over which it provided only one estimate of mean snowfall. So in this study, what we really wanted to do was figure out how we could actually downscale from the 6 kilometer estimate of mean snowfall provided from WRF to the actual 25 meter resolution that we care about in this simulation. And one of the most popular ways to do this is to use some sort of terrain-based downscaling method. Specifically, we investigated this approach where snow deposition at every grid cell was defined by mean snowfall, in this case from WRF, multiplied by a precipitation factor in space defined using an elevation difference here between WRF mean elevation and the true elevation of the terrain. So for instance, what we see is that at grid cells where WRF elevation and the true terrain elevation agreed, snow deposition at those grid cells were just simply mean snowfall provided from WRF at every time step. However, for grid cells that elevations below this WRF mean elevation, snow deposition was actually reduced by a precipitation factor of less than 1, and the opposite was true for true elevations that were above the WRF mean elevation. So simply put, this assumed that increases and decreases in snow in space corresponded with increases and decreases in elevation at spatial resolutions smaller than WRF here, which we know isn't always the case in this complex mountainous landscape. So we really wanted to compare this terrain-based downscaling versus this idea about pattern-based downscaling. Specifically, we wanted to use this method posed in a 2016 paper in the Swiss Alps, where the authors took distributed snow depth observation, much like we have here from LiDAR, and defined a precipitation factor based on snow depth at every grid cell normalized by mean snow depth across the domain, as shown by these subplots. And in doing so, they define snow deposition much like the train-based method, using mean snowfall, in this case for MORPH, multiplied by this precipitation factor in space. How it should be mentioned here that we're actually downscaling snow input in space as a proxy or a substitution for all the effects that actually increase and decrease snow depth in space. And if snow depth patterns are repeatable from season to season, this suggests that patterns from previous years may be able to downscale snow deposition in following years, or maybe even in real time. So we had two overarching questions in this chapter. We first wanted to ask, how do these train-based and pattern-based snow deposition downscaling compare? And which is the source of, which is the dominant source of model errors? Is it related to these snowfall biases from MORPH, or is it instead related to the resulting snow heterogeneity and these two different downscaling approaches? So to hop into the results, what I'm showing on the top row here is LiDAR observed snow depth on 7th of April, 2014. And the next two rows are snow depth on the same day downscaled using mean snowfall from MORPH, but one downscaling using this train-based downscaling and the other using pattern-based downscaling using a snow depth pattern from 2014. And to look at these a little bit more closely, we see that the train-based downscaling method that didn't actually intend to resolve these more complex processes that influence how snow is distributed in space tended to model snow that was too spatially homogeneous and had a poor coefficient of correlation. This is compared to the simulation with pattern-based downscaling, which had significantly better spatial distribution of snow and a coefficient of correlation of about 0.76. Yet despite this, we saw these simulations had a fairly large mean absolute error of about 24 centimeters. And specifically, they tended to overaccumulate snow in deep snow regions and underaccumulate snow in shallow snow regions. So to kind of demonstrate why this is happening, let's assume for the moment that we have two grid cells, say here across the stubble field domain. And these two grid cells have equal snow depth. And according to the pattern-based downscaling, that would mean that these two grid cells actually receive equal amounts of snow input. Yet we can see for this grid cell on the right that is in a warmer, more exposed location, and may have denser snow and perhaps some water lost to snow melt. You can see that that grid cell would require significantly more snow input to achieve that snow depth than a grid cell in this colder shaded region with less dense snow and no snow melt. So to just put this another way, the pattern-based downscaling assumes a linear relationship between snow depth and the snow input that was required to achieve that snow depth. Yet we know different grid cells in each of these domains require deviations from this linear relationship. So for instance, at lower elevations, shown here in the red on each of these hill shaded maps, we actually saw that many of these grid cells received or had snow melt prior to 7th of April, 2014. And as a result, those grid cells actually required more snow input to achieve some snow depth here shown by D0. And the opposite was true on higher elevation shaded north facing slopes, which had no snowmelt and less dense fluffy snow, and as a result required less snow input to achieve some snow depth D0. To kind of summarize our findings here, we found that overall for the pattern-based downscaling, winter snowmelt and snow sublimation in this year and in these domains had about 8 times larger impact on the spatial heterogeneity of the precipitation factor than the spatial variability in snow density. So this was a major issue for our simulations. So far, I've been really showing our ability to capture snow distribution at peak snowpack timing, but we can also take a look at how this distribution has an influence on how snow melts throughout the snow melt season. So what I'm showing here is total snow depth volume on the y-axis, so snow depth volume summed across the 3 domains, as observed by LiDAR, shown by these red crosses, and simulated using 1 simulation with terrain-based downscaling, and 3 simulations with pattern-based downscaling using snow depth patterns from 3 different years. And what we see is that on 7th of April, 2014, there was very strong agreement in snow volume between all simulations, and they actually agreed with the LiDAR observation fairly closely as well. So to us, this suggested that domain mean snowfall provided from MORPH prior to that date was relatively unbiased. As we marched forward throughout the snowmelt season, we started to see some interesting differences between these simulations. Specifically, those simulations with more homogeneous snow tended to melt far more rapidly than those simulations with more heterogeneous snow. However, we had a significant error that was introduced late in the spring snowmelt season by a spring snowfall event, shown here by this vertical dashed line. And specifically what we saw with LiDAR is only a very small increase in total snow volume after this event, yet all of our simulations spiked considerably. In fact, to the point where during this mid-May period, the difference between simulated and observed snow volume was significantly larger than the difference between simulations using different downscaling or the pattern-based downscaling using snow patterns from different years. So to briefly summarize some of our big findings in chapter 3, we found overall that the pattern-based downscaling was promising, but it was influenced by a number of errors, specifically on a first order by these coarse scale snowfall biases from WRF in this case, and on second order by changes to the precipitation factor in space that were influenced by things other than spatial differences in snow input. Here we're talking about things like winter snowmelt, winter snow sublimation, and snow density spatial variability, and on a smaller order by interannual changes in these snow depth patterns. Yet, despite these issues, we still found that these simulations using pattern-based downscaling tended to improve the spatial heterogeneity of modeled snow depth significantly as compared to these more commonly used terrain-based downscaling assumptions. So in chapter 3, we really showed that there is huge merit to this pattern-based downscaling, but it's still subject to some errors shown here on the bottom. So in chapter 4, we really wanted to ask, can we improve the results of this pattern-based downscaling, specifically using different data sets at our disposal? So before hopping into this, I want to acknowledge that this is a manuscript that's currently in preparation for a journal submission. And like I mentioned, we're going to be expanding out of only the upper Tuolumne River watershed to also include the Sage Hen Creek watershed in the northern Sierra Nevada near Lake Tahoe, and the Upper Kings watershed in the southern Sierra Nevada. And in this chapter, we're going to be using information at our disposal provided by snow pillows. So for those of you who aren't familiar with snow pillows, these are simply, you can think of these as scales that measure the weight of the overlying snowpack and use that information to actually calculate SWE. And the spatial location of these snow pillows can be shown by the dots and triangles in this leftmost plot. We also used information at our disposal from the Sierra Nevada Snow Reanalysis product. This is a product developed by Steve Margulis and group out at UCLA. It's more complex than this, but a simple way to think about this is it's actually a model product that uses different model parameters and different meteorological forcing to simulate several different estimates of the snow, shown here at a point by these different gray lines. It then also uses information from how satellites, in this case Landsat, sees snow cover disappear throughout snowmelt, shown here by fractional snow cover area over the Sage Hen Creek watershed, to actually go back in this simulation and reweight those individual ensembles and more closely correspond to the satellite observations of snow disappearance on a grid cell by grid cell level. Like I said, this is a little bit complex, but I'd be happy to answer or try to answer questions about it later on. But for our purposes, what we have with this product are daily estimates of SWE at 90 meter spatial resolution between 1985 and 2016. So to briefly revisit what we did in chapter 3, we calculated a precipitation factor using snow depth at every grid cell normalized by mean snow depth. And when downscaling using this precipitation factor, we assumed that spatial differences in snow depth were due only to spatial differences in snow input. But we know for this case that winter snow melt and snow sublimation and snow density spatial variability also influence the spatial variability of snow depth. However, here using this reanalysis from a historic date, say late March in 1996, we can actually calculate precipitation factor using this SWE product, or SWE at every grid cell normalized by mean SWE across the domain. In doing so, we have a precipitation factor that's no longer influenced by spatial variability in snow density. What's great about this product also is it's not just providing single dates in history where we have a SWE distribution, but it's actually providing daily temporal evolution of the SWE as shown here. So using that information on a grid cell by grid cell level, we can actually calculate the SWE accumulation up to a date, including that mass that was lost to things like melt and snow sublimation. So here, if we were to instead calculate a precipitation factor using SWE accumulation at every grid cell normalized by domain mean SWE accumulation, we now have a precipitation factor that's influenced by neither snow density or snow melt or snow sublimation, which we knew were major issues in chapter 3. However, it's worth mentioning that this reanalysis uses observations of snow disappearance to actually retrospectively or reanalyze what the snow must have been. So this is just to say that we don't have this product at our disposal in real time. So here we want to ask, can we actually use real-time information to actually go back in time and identify periods with similar SWE accumulation from previous seasons? And we tested several different ways to do this, but for the purposes of this presentation, let's revisit this thought that how SWE is distributed in space is a function of these both overlapping accumulation and depletion processes, each of which have some mean and standard deviation. And fortunately for us, especially in mountainous terrain, for periods near peak snowpack timing, how SWE is distributed in space tends to be a function predominantly of snow accumulation as opposed to depletion. And that suggests to us that we should be able to use real-time observations that come to our disposal, such as an observation from Landsat of fractional snow-covered area, shown here, to actually back in time search for a period with similar snow distribution, say here on 14th of April, 2004. And when doing so, we found that periods with these similar snow distribution tended to have very similar SWE accumulation patterns, shown by these two dates. So great, so if we have this historic SWE accumulation pattern, say here from 2004, we next wanted to ask, can we actually use this relationship between this pattern and real-time observations like those that we have from snow pillows to actually estimate watershed scale mean snowfall? So to provide an example of what I mean here, let's assume we have some snow pillow observation at a point, and SWE accumulation at that snow pillow may look something like this, as shown by the blue line. And of course, that's only particular to that point in space. However, now provided this pattern, we could put that pattern, that snow pillow observation in context with domain-wide conditions. Specifically, at that point, our pattern may say that domain mean SWE accumulation is about 5% larger than what's observed at this snow pillow. And then hopefully it would look something like this, as shown by the gray line. And we can do this not only for one snow pillow observation, but multiple snow pillow observations, as shown by all these different gray lines. And assuming some sort of normal error, we can hope that the median tendency of these estimates would be close to what is actually occurring across these domain-wide watershed scales. So to show some results from this, what I'm showing in this plot on the left is domain mean SWE accumulation biases in percent as estimated using the relationship between these snow pillows and historic SWE accumulation patterns from this reanalysis. And what we can see is that 75% of these estimates from 1985 to 2016 fall approximately between plus or minus 13%. And while that may not seem impressive, it's important to note that these biases are well smaller than some of our more popular or more commonly used atmospheric models and gridded precipitation products, particularly in the California Sierra Nevada. So to recap our questions, we found that FSCA could actually be used as searching criteria to go back in time and identify periods with similar SWE accumulation patterns. We also found that the relationship between those SWE accumulation patterns and real-time snow pillow observations could be used to infer a pretty unbiased estimate of watershed scale snowfall. Therefore, we think that we could actually use these better estimates of both snow accumulation patterns and domain mean snowfall to improve our pattern-based snow deposition downscaling that we talked about in chapter 3. So to show a brief example of that, what I'm going to show is our ability to recapture 1st of April SWE as estimated from LIDAR, specifically using this pattern-based approach, here using a SWE accumulation pattern from 2004, and domain mean snowfall estimated from the relationship between that pattern and several snow pillows. We also wanted to compare this versus a more commonly used approach, specifically using a domain mean snowfall provided from a product called NLDAS2, North American Land Data Assimilation System, which is a commonly used meteorological product, and downscaling using this idea of terrain-based downscaling that we discussed in chapter 3. So to dive into the results a little bit more, what I'm showing on the x-axis is SWE versus terrain elevation for the LIDAR estimated SWE on 1st of April, 2016. And what you may notice is a significant amount of SWE variability at all elevations, but SWE tended to increase on average to about 3,100 meters beyond it, which it tended to decrease on average. However, for the simulation with terrain-based downscaling, we saw far less spatial variability in SWE with SWE that only tended to increase on average, and as a result, really overestimated SWE, particularly at these high elevations. And this is compared to the simulation with pattern-based downscaling, which better resolved both this SWE spatial variability and this increase and decrease in mean SWE with elevation. So in this chapter, we really found that dates with similar SWE accumulation could be identified in real time using FSCA observations that come to our disposal, such as we have from satellite observations. And we also found that, using these historic SWE accumulation patterns and real-time observations from snow pillows, we could actually infer domain mean snowfall to accuracies well within most of our commonly used atmospheric models and gridded precipitation products. And in doing so, we were able to actually improve our estimates of SWE simulated using this pattern-based approach that we first discussed in chapter 3. So with this, we really wanted to discuss some of our major findings that we found in this research and some directions for future research that we would be very excited about. Specifically, I'd like to start by mentioning that how we're downscaling precipitation using these products is not a new idea. In fact, people have been doing this with gridded products such as Prism, as shown here, for many, many, many years. However, what we have here at our disposal from these reanalyses are much finer spatial resolutions, and perhaps could even go to finer spatial resolutions than what we have here using different satellite observations. And as I've already shown, this heterogeneity of snow has a very direct impact on the timing and duration of spring snowmelt, which is important for operational purposes. Also, these more commonly used products often rely on station observations in mountainous terrain, which are commonly located in regions of easier access, and therefore don't really observe these high extreme elevations of many mountainous watersheds, therefore resulting in some uncertainties. Yet these reanalyses use information from satellite observations, which should be theoretically viewing all mountainous terrain elevations equally. Additionally, as we discussed in chapter 4, as opposed to some product which is averaged over a long-term time period, we should be able to use this reanalysis in real time to actually go back in time and identify these periods, one or several different snow years with similar SWE accumulation patterns, and hopefully improve our estimates of SWE spatial distribution. We'd also like to recognize that perhaps one of the greatest benefits to this research was our ability to estimate domain mean SWE accumulation to accuracy significantly better than some of our more commonly used atmospheric models and gridded precipitation products. And to us, this really suggested that there is huge merit to these snow pillow observations. And specifically, we think that considerable time, effort, management, resources should go towards actually managing and perhaps even extending these snow pillow observational networks, not only in the Sierra Nevada, but in all mountainous regions. Along with that, though, we also realized that we did look at the California Sierra Nevada, which has storms come with very repeatable trajectory from year after year, and therefore may have SWE accumulation patterns that have more repeatable patterns between years. So what we would really like to see is the work presented that we did in chapter 4 in locations that may have less repeatable SWE accumulation patterns. And specifically, we realized that the reanalysis we used, versions of this have been run in other locations, such as the South American Andes and the Asian Himalayas. So these would be exciting places to test the feasibility of this approach that we discussed in chapter 4. So with that, I will wrap up, but certainly not before thanking a whole lot of people that made this all possible. And I'd really like to say a huge thank you to the UW Mountain Hydrology Research Group, both current members and past members. I've learned so much from all of you. It's been a wonderful experience. And I've really missed the time just hanging out in the office with all of you during quarantine, and I know I will miss that in the future as well. I'd also like to thank my friends, both in the Seattle area and outside of it, and you guys have all made this experience such a great experience. I'm going to miss so many of you. And I really want to thank my family for being so supportive, and especially my partner, Maggie, who's stood by me through all the numerous ups and downs of graduate school. So with that, I will wrap up, but I would be happy to take any questions that folks may have. Thanks.
Clapping on Zoom. So does anyone have questions for Justin? you may either type in chat and I will read it, or you can unmute yourself and speak up. So Steve says, your work is a major advance in mountain snow hydrology. Thank you for your highly informative and excellent presentation.
Thanks so much,
Not
Steve.
a question.
Nice to have you here.
I'll ask a question if no one else wants to jump in. So Justin, great work. Very informative. I really enjoyed it. One question I had on your latest chapter is, so snow-covered area, one of its downsides is that it saturates, at 100%. And I'm wondering if that limits some of this pattern recognition, and whether other variables could maybe be embedded in that idea that might have a broader range and therefore allow you to maybe leverage patterns that aren't just tied to snow-covered area.
Yeah, that's a really great question. This is something we looked at. As you mentioned, if it's 100% snow cover, that really doesn't provide us information about snow depletion in that time, right? We just know that area is fully snow covered. So, if we use these observations that have large portions of the domains are either fully snow covered or not snow covered at all, that really does limit our information. We're told the most information at these grid cells that are incremental or partially snow covered. And actually, we looked at this in this domain. We used a multilinear regression across these three domains using information not only from fractional snow covered area, but seasonal information that could be given to us from snow pillows in real time. So these include things like the number of snowfall events, the average snowfall per snowfall event, the amount of snowmelt that occurred before some observation date, all these information that we could actually have in real time. And what we found across these different domains were really different results. Some domains depended on some variables more than others. And overall, when including this multi-regression model, we weren't able to do any better. Actually, we did worse than if we actually went back in time and selected this period with most spatially correlated FSCA. However, as you mentioned, we did better if we didn't pull a Landsat observation from peak snowpack timing, but instead for a couple weeks after peak snowpack timing, where particularly at these lower elevations, we started to see this more less fully covered snow pixels. Does that sort of answer your question?
Yeah, that's a great answer. Appreciate it. Thank you.
Thanks.
Anyone else? Here we go. It looks like, I think this is Mike Dettinger. Are those just listed, the meteorological considerations that you mentioned, being able to include in picking patterns and analogs, or can you use something higher in the atmosphere?
Yeah, it's definitely possible. When you say higher in atmosphere, are you referring something like a model product that would be provided from WRF, or is it instead some sort of observation like a radiosonde or a some sort of weather balloon observation? My inclination would be that is if you go more towards these observations of the actual storm dynamics, from these atmospheric observations, you may actually be able to improve your representations of snow events between seasons, perhaps even like Doppler profiles. Yeah, it's a really good question, something I should definitely consider. Like I said, we did take a look at, I probably sunk a couple of months into trying to take a look at machine learning methods to actually pick these patterns from previous years, and none actually did better than just picking fractional snow covered area observations from previous seasons. But I think there is some considerable work that could be done on identifying these analogs.
Yeah, if I could just say, what I was getting at more, I suppose, was something a bit simpler than the full storm dynamics and things like that. And given my background, what I had in mind was just sort of the directions and intensities of the vapor transport into the area. You know, something like that that could be kind of boiled down to a couple numbers that would describe essentially every day, you know.
Yeah, I think that's a really good point. I know this makes me think a lot of what Jessica did in one of her papers, which showed that, you know, precipitation followed this prism map very closely, except for this one specific storm pattern that followed, I think, a high pressure ridge or something like that. So yeah, as you mentioned, you might be able to take a look at these seasonal differences a lot better using these sort of storm patterns. I think that's a really good idea.
It's great stuff.
Yeah, Justin, this is Glenn. So as part of your master's degree and your PhD, you've used both physically based kind of snow evolution, spatially distributed, physically based snow models, and you've also looked at kind of observation-based approaches. What can you say about how your observation approach, how can that be used to improve deficiencies and weaknesses in the physically based modeling approaches?
Yeah, I think that's a really great question. And it makes me think a lot about Matthew Sturm's paper in 2010, or Sturm and Wagner, where they actually took a look at these repeatable wind-blown snow patterns. I think they actually used Snowmodel and used that information from year to year and an ensemble of simulations to actually calibrate the parameters that more were responsible for the spatial distribution of snow. So I think, you know, like I said, this observation-based approach that's more statistical in nature may be really practical from a management standpoint and able to be applied today. But our physical representations of these processes and models are getting better and better every day, and our computational ability to run fine simulations is also getting better. So there's a lot of information provided from these historical patterns that could be used to better improve our simulations, specifically in these areas where we don't have a lot of ground-based observations at our disposal. So I think this is valuable both from a model improvement standpoint and a real-time standpoint for something that could be used to, say, forecast stream flow in a spring period.
Great, thank you.
Thanks.
And in chat, Michelle wrote, amazing job, Justin. I know your recommendation was for more work in different locations under different conditions, but do you have any thoughts, or could you comment a bit more on the utility of your pattern work in highly atypical years, such as with large abnormal storms?
Yeah, I'm actually really glad you asked this question because in this research, we found that there was a really low snow year in the Sierra Nevada, water year 2015. It was historically low. I think some estimates had a return period or a period of duration between a year with similar snow of about 600 years. So it's very, very abnormally low snow year. And using our reanalysis, which covered these 31, 32 years, we weren't able to actually go back in time and actually find a period that was very representative of the abnormal conditions in that year. And that's more representative of the differences in the seasonal snow as opposed to, say, one snowfall event. But yeah, as we grow this reanalysis data record, we should be able to represent more seasons with abnormal conditions, but we still may be limited. So that's a really good comment. There is less flexibility to represent these years that don't look like any other year in the record.
And Steve writes, your pattern disaggregation approach is similar to a deterministic spatial Kalman filter. This is clever. I don't know if you need to comment on that.
Well, thanks. I appreciate the compliment.
Anyone else? I don't see anything else in the chat. Nicoletta's got one. Following Michelle's question, what are your top recommendations to apply these methods for improving watershed scale simulations of stream flow?
Yeah, I think there's some significant merit to these reanalyses. And these reanalyses use information at our disposal that we should have in all mountainous snow-covered landscapes. So I think this is an incredibly underutilized data source. Specifically, for high regions of mountainous watersheds that aren't observed very well. So I think these reanalyses should be used as a baseline, like I spoke to Dr. Liston, both for improving real-time estimates from like a watershed management standpoint, and also a way to actually better resolve our physically based models in complex terrain. So I would really recommend that, these reanalyses be performed everywhere with snow. They're very, very exciting.
And Mike says, amazing work. I can't wait to see what you'll do in years to come.
Thanks. And thank you everyone for being here. Really excited by this awesome turnout.
So last chance for questions from anyone in the general audience. All right, then I'll let Justin people are saying congratulations. Anyone who wants to just unmute and say hi to Justin, you're welcome to. And then I'm going to ask, I will ask everyone who is not on the committee to log off. And then we'll take a brief break after that. But right now, just if you want to just say hi in the chat. I think chat is kind of the equivalent of applause these days.
Hey, Justin, it's Dennis. Well done.
Thank you so much. Thanks for coming.
Also, I'm stopping recording for people who